So last lesson we talked about, we gave a basic overview. We talked about, we kind of focused on this one where we looked at the limitations of the Arrhenius theory and the Bronsted-Lowry theory. And things that we skipped over were the neutralization reactions. And we also skipped over the idea of indicators, the primary or the first way that we detected pH change or different concentrations of hydronium ion. This is first using chemicals, and now we use the pH probe, which uses conductivity. Okay, so we're going to first look at indicators. So an indicator is a substance that it's similar to Mod 5. So in Mod 5, a lot of the reactions that you learned were about chemicals that had a color on one side of the equation and a color on the other, and that was really useful because we could learn about the micro scale from a macro property like color, right? And so an indicator is itself a weak acid and its conjugate base, or vice versa. So this is a weak acid. It's an acid because it can donate a hydrogen. Right? It's also weak because indicated by the equilibrium arrow. And this base is its conjugate. It's its conjugate because it differs by a hydrogen. It would have the same chemical formula but differing by a hydrogen. And essentially, because it can gain and accept hydrogens at different levels, what I mean by levels, is different levels of hydronium ion. Right, because remember this will have a Ka associated with it, and each indicator will have a different Ka, a different ratio of products to reactants. So an indicator is a color when it's got the hydrogen attached, and a different color when the hydrogen's not attached. And if you go put the indicator in a solution that has, say, a lot of hydronium ion, then it's very likely it's in the form of this, and that will have a certain color. Right. This bit here is a bit of an extension. It's talking about colored compounds having conjugation, which is when you have single bonds, double bonds, single bonds, double bonds. And essentially conjugation is a big reason why it's a colored compound. Now, you can go into a bit more if you're physics inclined and read about it. So conjugation, I just mentioned the word conjugate in relative terms for a chemistry. So in chemistry right now, I'm talking about conjugate an acid and its conjugate base. But you can also have this type of conjugation. And that conjugation is double bond, single bond, double bond, single bond. And the quick gist of that is, well, if I go down and use this as an example, this one. In this example of methyl red being protonated, okay, so you might notice that this is where the proton is. When it's got the hydrogen attached, it's red, and when it doesn't have the hydrogen attached, it's yellow. And you'll notice throughout the whole compound, there's this alternating double bond, single bond, double bond, single bond. Essentially, once that hydrogen goes off, instead of a charge remaining around the nitrogen, because a H plus left, that charge is able to spread throughout the whole molecule. And because it's able to spread throughout the whole molecule, it's very unlikely that a hydrogen will come back to that area that's got a lot of negative charge. So this idea of resonance and conjugation, which is an extension of the course, allows charge to be spread throughout, which decreases the reactivity of the substance, and because it's decreased, it changes how well it accepts a H plus back. Okay. It also lowers the energy required to excite electrons, okay, and instead of instead of the energy being in the ultraviolet light, like a lot of white compounds are, the energy required to excite electrons to the upper orbital and back is typically in the color spectrum. Okay. All that's an extension, and you can kind of tell I'm wanting to move on from that. Right. An indicator. So if you haven't guessed, IN is indicator, is HIN, and this substance here is huge. This methyl red substance here is huge, right? And I would write H, and then the rest of it is indicator. Okay, so the indicator is literally the rest of it, and this one is I minus, absent from the H. So what do you need to know? Indicators are weak acids and conjugate bases, or vice versa, because you could call that the weak base and that the conjugate acid. And they're different color when they're protonated and deprotonated. And that's very useful because then I can stick the indicator in a solution. Say it had a lot of hydronium ion, then my indicator will, because these two will bump into each other a lot, the indicator will mostly be in HIN form, protonated, and that indicates to me that that solution is acidic. And if I do a whole bunch of tests, you can start to see, if you had, say, 4 indicators and you put in your unknown, let's say your unknown was pH 8, but you didn't know it, you would put it in a bunch of indicators, and if you got heaps of indicators, you go, well, it's blue for him, it's yellow for him, it's not quite pink, it's colorless for phenolphthalein, and it would be just blue for this bromothermal blue. And if you do enough, okay, if you figured it out, all of these are above 8, but because it didn't turn pink, I would know that my pH range was between 7.6 and 10. Okay, and if I got another indicator that perhaps changed color after 9 and it didn't change color, I could narrow the range from 7.6 to 9. And you get enough indicators and you can get a narrow range of what your solution, your unknown solution that you're putting the indicator in, you can get a very good grasp of what the pH is. Now, this is all like olden day technology, so to say. It's cheap and easy, so it's still used today. But nowadays, we just use conductivity to measure the hydronium ion concentration. So we have a probe that measures, that firstly only allows H3O plus to get in there, so it's a selective membrane that only allows hydronium to go into the probe area where then it measures its conductivity. So pH probes are far more accurate, but you still need to use indicators or learn about indicators. Right, that's all I'm going to say on indicators, but there's some other examples here that kind of show the same thing for all the different indicators. Here's a bit on like the dot point about where do we do neutralization in the world, in everyday life, and in the industry. Okay? That's more of a read process. You can pause and read. And now we're talking about enthalpy of neutralization. So for this, I might just do a question. And I've got some questions down here. And there's some solved ones there. But I'm not going to get you to pause and do that. I'm just going to do a blank one by myself. So, we're now asking, when I mix this acid, sulfuric acid, with this hydroxide, what is the enthalpy change? Okay, so we start at some, the electrons start at some energy. The enthalpy of neutralization is always exothermic, so I'm always going to finish down. And I'm trying to find to what magnitude is my difference in enthalpy. What magnitude is my difference in enthalpy? And we've got the answer down here, and it says theoretically this couldn't happen. So this question is purely for just doing the calculations. So let's just understand that firstly. And a lot of people, when they do these questions, they write out the reaction like this. Okay, it's actually in a lot of textbooks. They go acid plus base goes to salt plus water. And you can answer the question like this. I don't teach this way. Okay, by the way, I haven't even considered balancing, and I think that's balanced there. I don't ever get if it's enthalpy of neutralization, I never get the kids to write out this as their reaction, because the true reaction that happens is the hydronium ion bumping into OH minus and becoming two waters. Now, that means all you need to figure out is how many hydronium ions you have. And in this case, it's going to be 2 times the moles of H2SO4 because it's diprotic. That's to say, it's going to produce 2 lots of H3O plus if you go right out its ionization reaction with water. And so it's going to go 2 times C times V, which is going to be 2 times the concentration, which is 1.6 moles per liter, times by 35 mils, which is 0.35, right? And that will give you a certain number. Moles of hydroxide is going to be equal to the moles of KOH, 1-to-1 relationship, is equal to C times V, is equal to 2.3 times 0.01, okay? And that equals a certain point. And I'm going to have to do this on my phone. I didn't bring that, so you're going to have to excuse my calculations. For the first one, I'm doing 2 times 1.6 times 0.035, and that's equal to 0.112 moles. And then for the next one, I should be able to figure that out. I'm pretty sure I just moved it down 2 decimal places, but just double checking. 2.3 times by, times by 0.01. That equals 0.023, like I thought. Should have backed myself, right? And it should be pretty obvious if they're in a 1-to-1 ratio that my reaction is limited, okay? In fact, my reaction is limited by hydroxide. So the amount of water that's formed, produced, is equal to the moles of KOH that reacted, okay? Or the moles of hydroxide, doesn't matter, they're going to be the same, equals 0.023. And what I've essentially established is this is how many moles of water, this is how much the reaction happens, and therefore this is how much of the reaction is contributing to my temperature change. So we're going to come back and use this very soon. For right now, we're just going to go back and use familiar reactions like Q equals MCAT. For this one, we're trying to find so this is the energy released or the energy absorbed. It's got a kind of semantic of whether it's a negative or not. So this is the energy released by the reaction. And then we're going to divide it by how many moles and get the enthalpy change. So my mass in this one is, you assume that even though we don't get given their densities, we're just assuming that even though we've mixed in some acid which would change its density, we're going to assume the density of water. So if we see 35 mil, we're going to change it to 35 grams plus 10 grams from this, so that we've got a 45 gram solution. We're going to use C as 4.18 joules per gram per Kelvin. Okay. And and then we're going to times it by the temperature change, which was 12.4 Kelvin, which is also the same as 12.4 degrees Celsius, because it's the difference in change on the same scale. And we got 45 times 4.18 times 12.4, and that's going to tell me my energy released, and I'm going to have to convert that to from joules to kilojoules. So 45 by 4.18 by 12.4, and that's 2,332.44 joules, which is going to be 2.33244 kilojoules. And the last little bit is the enthalpy of neutralization is equal to negative Q on N. And I've got negative 2.33244 by the amount of molecules of water formed, which is actually the definition. This is the energy released per 1 mole of water formed. Okay. My moles of water formed I calculated earlier to be 0.023. And so I'm going to do both those things on my calculator. Divide by 1,000 and then divide by 0.023. And that gave me negative 101.41043. My lowest sig figs in my reaction is 2, even though that's ambiguous. And so I should be giving my answer to 2 sig figs, which is hard. Considering it's too hard for this one, like I should be going negative 1.0 times 10 to the 2. And the units of this, that's kilojoules. This is mole, so this is kilojoules per mole. Okay. And you can do this type of reaction for all of them. So what I mean is, no matter what the acid, no matter what the base, enthalpy of neutralization doesn't work if you're using a weak and a weak, by the way, but you can do a weak and a strong, so at least one of them has to be a strong. I wouldn't worry about that. They're not going to test you on that. They haven't kind of explored that in any of the dot points. The other thing is, all you got to do is kind of keep note of what's diprotic and whatnot. So if this was HCl, this would be a 1-to-1 relationship, and I wouldn't need this 2 here. But essentially, this is my method. I'm sure other teachers use it. This is my method to shortcut it. If you do it how the textbook says, there's a few more steps. So this is my easy way. This way will actually help you for another type of question that is very similar. In the next inquiry question, we get you to figure out the pH of the solution. So in this case, I had an excess of 0.12. I have an excess of hydronium ion. And if I minus 0.112, if I minus that from that, there's 0.1. So how much H2O plus I have minus how much reacted, I can figure out the moles of hydronium that I have left over. And then I can figure out, I divide it by volume, and I have the concentration of the hydronium ion. And then I plug it into my pH equals negative log of my concentration of a hydronium ion. So inquiry question 2 will use this same idea. In this question, we're treating it like a limiting reagent question. In the next one, we're trying to figure out how much is left over. So it's the same idea, and it just splits after you figure out the moles of each one.